All right, so this is the next talk, the last talk of the day, as John said. This is Minge Xie, a statistician from Rutgers University.
Thank you, Larry. Well, thank you, Larry, for chairing my talk. Really honored. And then thank Mikhail and then Anne for having me over here. It is my great pleasure to be back again, this time in this international interdisciplinary platform. I'm new to STEMs, and then I came here to learn, and then also hope to make some connections. So far, I'm having a good time. I think it's a really wonderful workshop. For many of you who I have not met, I work on foundation of statistical inference. Particularly in recent years, I have been working on this artificial sample-based inference approach called the Repro samples method, and then has connections to your simulation-based inference, really close connected. And originally, I was planning to give a talk about our new work on how to use Repro samples method to make inference when my model is misspecified. And then, kind of a couple of weeks ago, I realized that this workshop is more like the disciplinary. So I kind of went back to to give a talk, one of our earlier works, maybe one of the oldest work, and then trying to talk about tell about the ideas behind the development. Hopefully, will be kind of for people. New friends will be a little bit better suited. And I also apologize for those who were in my talk 2 years ago. I have recycled some slides, so I apologize for that. And also I apologize that I'm very good at making typos. So if my new slides have typos, I rushed in last couple of days. So please excuse me first, kind of apologize for that. So what is the Repro samples method? Let me give you a sort of intuition first. Slides is that we create and study the performance of artificial samples that are generated by mimicking the true observation and use that understanding to kind of help us to do the inference. The Repro actually in our mind is reproduction samples. So it's kind of artificial data. We try to distinguish other kind of simulation-based kind of samples. The features of this method is that actually containing both finite and large sample results. It does not require this likelihood function. Of course, you can use it, but you don't have to use likelihood function. And does not need to rely on large sample theory. That's no regularity condition, like Larry's universal inference. And this works for any types of parameter, including discrete types, for example, a number of layers and then things like that, even objects for the discrete parameter, and also works for any types of data. It could be numerical imaging, a graph, even voice, etc. I think I may have a time, if I skip some of the technical details, to talk about the relation to Bayesian, to Neyman inversion of classical hypothesis testing. The original, actually, at the beginning, when we start to work on that, actually, I was thinking is that trying to some of you may know that we have this group so-called BFF, best friend forever. So this group, I was trying to do that ABC. I was trying to do frequency version of ABC. So with that group, kind of our belief is anything Bayesian can do, frequency can do, anything frequency can do, probably Bayesian has another version of it. So that's how we try to do it. So it's kind of try to do a Bayesian version of ABC. Indeed, if the simulation Monte Carlo version of Repro samples has a connection to ABC, but however, of course, we try to overcome two kind of issues in the ABC. One is that rely on sufficient statistics. If you don't have likelihood function, how do you know it's sufficient statistic? A second thing is the epsilon. Epsilon theoretically either go to zero very fast, And then, but if epsilon goes to 0 very fast, rejection rate is too high. It's basically computing efficiency is a problem. So we can say our method actually kind of resolve and sidestep these issues. And of course, this definitely has a connection to Anne and Mikhail's likelihood-free inference, and then Larry's SBI, especially robust SBI, really, which I look forward to hear about more tomorrow. This is kind of, I went back to this one of the two earliest kind of case study examples. What we used is basically trying to construct a 95 confidence set for the unknown number of components in a Gaussian mixture model. So, the number of components is discrete. How do you make inference of discrete inference? And then this is a data set, actually a couple of groups study actually more than a couple. Just this is two JASA publications of these two groups. One is from here, and the other one is Jiahua Chen's group in Canada. So basically, this data set, for this particular data set of n equal to 190, we can get a confidence set of the unknown number of components is 2, 3, 4. So we can get that one. And then with that, of course, 2 you have estimate, 3 you have estimates, and 4 has estimates. So this kind of listed on the table. The thing is that, of course, when we talk about that, we have theory proof that works. But then we also want to show you at the beginning that numerically it worked well as well. So in particular, we mimic that's real data setup with tau 0 equal to 4, basically taking the last row of this table as my parameter, true parameter, to simulating my normal mixture of 4 with 90 data points, and then this kind of repeated 200 times. The story is over there. I only 7 times I miss these. I didn't cover. Our simulation did not cover the choose tau equal to 4, but the rest, whatever 197 covers. So you can see that empirical performance is 96.5. If you use for this same 200 data set, if you use point estimates, first, it doesn't have uncertainty. The second thing is that even you do the bias tau hat, it's biased. If you use BIC, actually, only 2 times out of 200, you're getting the truth, recover the truth of tau equal to 4. So, and then Catherine Roeder and then the Jiahua's group, they did this kind of hypothesis testing, doing one-side hypothesis testing, inverting it. They get some confidence set, but they only have a low amount. Actually, the power we have numerical studies show their power is also not as good as ours. Okay, so this is actually a Gaussian mixture model. I know Larry and several of you have kind of studied on making inference for the number of unknown components. It's actually turned out to be very difficult classical inference problem is known, is a wacky problem, is that the model parameter actually changes according to different tau value. Different tau value, you have parameter length of unknown parameter is different. So basically, the parameter space varies with different tau value. So that's kind of, and also worst is that tau 1 in k equal to 3 and tau 1 k equal to 4, they don't match. They don't have like alignments of that things. So that's kind of make things really wacky. So this is another example, which I don't have time to talk about, but we have a paper finished, which is that in high-dimensional regression, this is basically classical high-dimensional regression, you do have a sparse model. So there are true sparsity of the true model. So the model parameter, actually, you're thinking altogether, it's not just regression coefficients, also the model choice. The model support on non-zero models is also a model parameter. So that parameter is non-numerical, right? It's kind of set of variables you selected. And what we will be able to do, let's just do a little bit of advertisement. What we will be able to do, get confidence set, 95 confidence set for the model selected model. So you have a true model. I gave you a confidence set of several models, and with confidence of 95, one of the model is a true model. And of course, we can do beta. And also we even can do the jointly beta and tau 0 and the beta. So, and I want to emphasize that this is a guaranteed finite sample. In the beginning, I think all the high dimensional regression models, they do large sample theory. And then we have both finite sample and large sample theory to cover that kind of model. And with that, we had a student to try to extending that to logistic regression model. So this is also on arXiv. And then this is actually C is the one we're trying to, I try to present, actually plan to present. And this is basically is that is a high dimensional binary classification model. I don't know the model structure totally, but I'm using walking sparse model to work on it, to fit it and then see how we can do the inference. So that's the, I will give a link for the arXiv paper. Also posted last week and pushed too hard, very hard for students to put it on the arXiv. So this is I give a link for that as well. And also our group have been working with different collaborators and groups of students and are working on different kind of applications or using this Repro samples method on other examples. The first two bullets actually seems natural. One is the change point detection with unknown number of change points. That's one also very similar to Gaussian mixture. And actually for tree models is similar. Tree model is actually, you can thinking is that if it's a regression tree, particularly is a Gaussian mixture kind of extension of mixture models. So this is actually, we have worked on that. Have students working on that, and then we have working on like ranking inference and things like that. We actually getting grants to work on this Markovian models, graphic network model, to looking at the nodes, and then also the other one is neural network model. How do we kind of do the constant quantification on these type of things? Okay, so this is kind of advertisement, a bunch of things, and then. These next few slides probably give you like kind of a setup and then also the main idea, what's doing the inversion, how we do the inversion kind of idea over there. So what we have here is that we have a generative model, assuming we know the generative model and have a known distribution. So here in this audience, I don't need to introduce what generative model is. And I'm writing this is a realized version. I particularly highlighted there is underlying realization of unobserved error. This is U-terms, okay? So the assumption of this be able to work is the assumption is very minor, is that given any theta, you will be able to you can generate in U, then you can generate in Y. That's all you need. That's basically that's what you need. And I don't need to go over all these models, tree models, differential equations, and also others. The inference goal is that to find 95 confidence set for the theta 0 or part of theta 0 or its function. Okay, here theta can be any type of parameter, continuous, discrete, mixture, or non-numerical. And then, as I mentioned, we just started working on this mix, not as deep as Larry was doing. It's just starting to looking at the misspecified model in the binary classification. And indeed, my belief is that similar to Larry's robust version of SBI, and then this will be we will be able to deal with misspecified model as long as we know how to define. The Larry called projection parameters. We're talking about, we're using the term oracle parameters. And then this is a kind of inversion idea, what we kind of first thinking about that. So I have a model of this. Then my realization is this, right? Observed data set, my target is the red theta 0. And then there's the realization, U real. But U real, I don't know it completely. I only know it's coming from certain distribution, so it's part of the knowledge. If I know the U real, of course I can get in the theta solving this. Suppose I can solve it, then I can get theta 0 out. But then if I cannot, if I don't know this, so what we will do is that we just assuming we first find a broad set, see what's the range of this. Because I know the distribution, I can figure out the broad set, the range of this kind of potential values of this U real. If this is if the U for any of the U star inside this kind of range, I would be able to generating my observed data. Then this particular theta is the potential theta value. You can don't rule out it is theta 0. So essentially, this is the interpretation. The idea of the inversion is very intuitive. Basically, for potential any potential target value theta, I don't know it's theta 0 or not. But if you can find a realization of the noise inside this kind of Borel set, so basically saying that I don't have a small chance, right? This is, if a Borel set, you're usually get rid of the small chance of use. If I control the small choice of choice, as long as I have this particular theta, I can find a U star inside this Borel set. I can generating my observed data. That's basically saying that my theta, I cannot rule out theta is theta 0. So this is very, very intuitive inversion. And this is basically, that's the simple fact. It's very just a few lines, you can prove it. And then in particularly, actually, what we propose, because this kind of a little bit limited of this version, it will particularly introducing the concept is called the new kind of a mapping function. We call it nuclear mapping function. It's very similar to test the statistic. So for any potential value you're looking at, you look at that's the distribution of this mapping function, you get to the Borel set, and you can kind of solving for this equation. And then this is also, it's very easy. You can prove this theorem. It's just even, I think undergraduate student will be able to, with probability training, can do this. So this is essentially, it's essentially what we were doing here. It's essentially utilizing this matrix. So it's similar to that inferential model type of things. It's this is kind of Fisher-Demps inversion type of idea getting over here. So this inversion, I was talking to Changhai Liu, and he said maybe we should call it Fisher-Demps inversion. So indeed, this is inversion method, but involving the set. So we call it Fisher-Demps inversion. If in a special case, the nuclear mapping can taking as a test statistic. If you nuclear testing to the test statistic, that method actually is highly relevant to the Neyman-Pearson, the Neyman inversion method. There's hopefully at the end, if I do have time, I will go over that. So this is just give you this slide. I think I gave that a couple of years ago. It's just I think this is just simple enough slides example to explain the Repro samples method. So basically, I have a data set coming from the binomial distribution. I have observation from this binomial distribution. The binomial distribution, of course, is easy right out of the generative models. And then if I'm taking this nuclear mapping as this function, this function, we know that because U is the uniform 0, 1, so this is essentially its binomial, I would be able to figure out for each given theta, I would be able to figure out the Borel set. And then with that, I will find out the particular Borel set. Okay, so this slide is kind of give you an idea. So the data set actual truth is that 10% is a 10%. The truth of data point, the theta 0 is 10% with 20 times 10. So it's a truth. So this is no larger sample theory. But I don't know this truth is 10%. What I do that me try theta potential value is 0.3. For the 0.3, we know it's binomial 20 and 30%. So this is kind of a bar chart of that distribution. So from here, it's easy to find out, get rid of those kind of small kind of tails. Then you will see that the Borel set is become 2 and 10. So this is essentially what we have to getting this Borel set. Okay, so this is kind of idea. I don't know that, I try it. So if I plug this Borel set into here, essentially I get my confidence set. It is like this. So in this example, basically saying that my Borel set for this nuclear mapping function is 2 and 10. If my observed data is between 2 and 10, I know that 30% is inside this confidence interval. Otherwise, data is not belong to. If my observed data is not between 2 and 10, it's like a 13, then it's outside of this, doesn't satisfy that. So then that 30% is not one of the value inside confidence interval. Is okay? So that's kind of idea is that you try even each different kind of parameter of interest, and you look at that one, what is the lower bound, upper bound, and you can kind of look at your observed data is within that range or not. If it's within, then do it. Otherwise, you don't. Okay, so that's basically that's kind of set, and then we actually, if I show the numerical result, you know that it works well, right? So otherwise, I won't have this table. And the particular ward actually has the issues with these two kind of non-asymptotic version. And then they are a fiducial, generalized fiducial is actually has a fiducial version from Jan Hannick's group, and then they also not performing as good as us. And then our method actually comparable with the STEM method, the classical STEM method. We know is the improvement of Klopper-Pearson method is slightly better. I think we probably cannot claim it. It's very similar. We just have one number is slightly better. Like this, the length is a little bit better. These two lengths extreme cases. But anyway, so this is basically that's the idea of the inversion idea. This Repro samples represented is okay. So I hope it is that. So in particularly the things I want to emphasize, we've spent a lot of time is working on this is kind of this class of non-trivial inference problems. Regularity condition does not apply. This method is that the parameter is a mixed type. The one of the parameter is discrete, like Gaussian mixture model is discrete, or even in the high dimensional regression model is non-numerical. That's a model set, right? And then remaining parameter are continuous. So this type of parameter is mixed, so we can write them out. So how do you deal with this kind of mixed type of problems? If you do it altogether, it's like a Gaussian mixture model is very difficult because the parameter space changes. It's kind of wacky. So how we deal with that, we kind of set it into steps. Our proposal is doing separately, looking at the discrete parameter and continuous parameter. For the discrete parameter, we first handle discrete parameter, treating the continuous parameter as nuisance parameter. You can deal with that for each given of this. And secondly, is that after you handle this one, for each given this tau k, you can kind of do this inference for the continuous parameter. So that's kind of make things a lot easier. Otherwise, you do it together, it's a problem. It's very, it's kind of hard problem, like Gaussian mixture. I just deal with the number of components first, treating the mu's and sigmas as nuisance. And then after I get the idea of this 2, 3, 4 is my Gaussian mixture, number of Gaussian mixture. For each of those things, I know how to deal with mu and the sigma. So that's essentially, that's the key of that kind of intuition, the idea behind it. The other one is that like in the high dimensional regression model, all the possible model choices is 2 to the p choice, right? The p is x covariant dimension, 2 to the p choice, and then it's too big a space to search around. So we use this again, using this kind of Bayesian inversion idea. I will talk about this technique to drastically reduce the search space of the discrete space. Okay, so for the Gaussian mixture model, it's not as big an issue, but for the model selection, for the high dimensional model selection, it is indeed the issue because 2 to the even p is 100. 2 to the 100 is so big a space to deal with all possible possible space of the models. So the technique of dealing with this discrete parameter space is I realized that, again, we kind of coming back to this estimating equation, right? It's just basically we realized we only have this observed one, and discrete parameter have third version of doing that. The idea is that I can use data-driven, find a data-driven small set of the on the discrete parameter space such that is almost 100% coverage for that one for small delta prime. So the idea is that inherited, when you do, so this is the equation, this is our data generated equation. If I really know the noise, my observed data is look like this, right? This look like this. And then nowadays, you solving these things, nowadays even you not complete solving this, you have a kind of a loss function, and the algorithms to kind of minimize this loss function, minimize the loss of that one. You look at this equation, you realize that if I put the true kappa and inside here, this actually, this is loss function is going to be 0 because kappa 0 and C0 give you this exactly equal to 0. So loss function equals 0. That's immediately give you kappa 0. So if I injecting this unobserved noise into pretending I knew it, putting this here, I would get in perfectly solving this equation, getting the target. And then, of course, this loss function can be extended to a more general case, just looking at the distance between the observed data and the artificial data. Look at the distance, and you will kind of getting those things. Of course, in this case, this ideal case, I observe the realized noise. In most of, in almost always, you don't see that. So instead of using the realized noise, let's do the theta star. I use randomly generating because I know it's coming from the distribution D. I just simulating one noise from the D distribution, and then I plug into this this algorithm. I will solving giving me one of the kappa star. Okay, and then this kappa star is actually realized this discrete parameter space. This one is kind of usually the noise is continuous space. So the U star is from uncountable space, and then kappa star is from countable space. So this tends to be many to one mapping. So it's because that space kind of dimension just kind of drastically reduced. So in that sense, we typically would have find a set, which is basically not only one U star getting equal to kappa 0, U0 getting kappa 0, but they are bound to have some other U stars in the neighborhood of UK. U star, U real will give me kappa 0. So that's basically the idea of many-to-one idea. That's essentially, this is the illustration of that idea is that I realized that one. So if I have generating noise lucky enough, it's in the neighborhood, then I will be able to kind of recover the kappa 0 as if it's U real. Yes. Oh, already 5 minutes? Sorry. Okay, so this is basically, that's the method and then doing that. So instead of boring the details, this is kind of the idea, you're targeting all these things and get those numbers out. So this is pretty much of the two-step procedure. So going through that is first make inference to getting the kappa discrete, the parameter, then reduce, and then that's basically use technique 2. Then for each of given in the data set, I'm going to make inference and aggregating them. This is the same thing why I do the Gaussian mixture models. I'm basically doing that get confidence set of 97.5% confidence set for the kappa 0. Then I do the inference of that. So that's just maybe let me skip those technical details of how I do the. But the idea, the roadmap is over here. All these technical details are in our paper, so you can go back to if you are interested in the technical details, you can go to see how we did it. Okay, actually, and then the numerical result is perfect. I still have 3 minutes or 4 minutes. Okay, so if that's the case, I'm just skipping all these things. And then one thing I want to emphasize is that even for the mu and then the sigma coverage, it's very difficult to problem in the Gaussian mixture because the membership assignment is very bad in the EM algorithm, and also tau 0 estimate is not accurate. So as far as I know, this is we're talking to the Jahuas group. They say they never getting as good result coverage than what we were doing. And then this is the basic last. So this is actually maybe 3 minutes quickly. I think people here realize may be interested in to see what's the connection to Neyman inversion method. So at the outset, I would say this is the performance of our confidence set, Repro samples confidence set, depends on the choice of the nuclear mapping function. The role of nuclear mapping function is similar, very similar to the role of test statistic in Neyman-Pearson framework. So in particularly, we can picking our nuclear mapping function as a test statistic. If we do that, we have a theory to tell us that actually our Repro samples is smaller than the inversion method in the classical method, and then it's never be large. In particularly with that is that as long as you can find something optimal using the Neyman inversion method, then our Repro method will recover the same optimal confidence set. So, and then also I will have a couple of slides to show that actually we do more than this Neyman-Pearson confidence set. This is basically give you an example with a very simple example with this kind of uniform -1, noise. And then if you use the Neyman inversion method, you get this confidence set, confidence interval using exactly confidence interval based on this distribution. And our confidence set, confidence interval actually is a subset of that because the constraint in the inversion automatically building into that. The numerical result also demonstrate that. And then we actually can improve the likelihood ratio confidence set. If you use the Neyman inversion, use likelihood ratio test. Likelihood ratio test is only optimal in a simple, very simple. When you do the intervals, actually is not optimal. And then we do have examples to saying that this is not the case. And then we can improve that. So basically, the lens, the coverage of both are pretty good. Our method of the lens is better. So it's the same example of that. The last slide of that one, I want to emphasize that the notion of nuclear mapping function is broader than a test statistic. This is an example. I don't know. Maybe a lot of smart brain over here. You might be able to find good summary statistics for this problem, but so far we thought that we cannot come up with a good test statistic for the inference problem, and we can only use the nuclear mapping function. This is non-parametric quantized inference with privatized observations. Basically, the setup is that I have yi coming from unobserved unknown distribution, the latent sample coming from the unknown distribution, but the observed the data set is privatized in the sense I inject the noise, like sensors inject noise to this y, and the noise they give you, this is actually normal zero delta distribution. So in particularly, your observation is the underlying latent y plus underlying unknown unobserved the noise of the privatization noise itself. Y real itself has a noise. So actually, if you look at this, the difference of these two is this whole thing is y, the latent y. The latent yi, because I'm looking at the confidence interval of this one, Q's quantile of this one, then it's essentially this generative model is that. The question is that in this particular problem, would you be able to come up with a good summary statistic involving the y tilde instead of what we do? We can have a method just using T and B without involving y tilde to do the inference. Okay, so that's all for mine, and then thank you so much of that one. This is the last slides, and then I do have uploaded one version online and then on the Google Doc, and then you can look at it, click into that. Actually, I talked about this a few years ago, but then the paper is still in the process. One is in my revision for JASA, the other one is minor revision for Amazon Statistics, the last two. Hopefully next year will come out pretty quick soon. And then I apologize if I'm slowness on this, but given I probably also have excuse is that most of papers like 80, 90 pages, including the appendix. And then our response to the referee report is over 30 pages. So that's kind of very slow on us and also doing all these things. But anyway, so the last one is that misspecified binary classification problem. Thank you so much.